In the second part of section 6.6, we're looking at a few more proportionality theorems. This first theorem says if three parallel lines intersect two transversals, then they divide those transversals proportionally. So I want to put some marks here to illustrate what's happening. We have if three parallel lines intersect two transversals. So the three parallel lines must be these three. I'll mark them as such, lines R, S, and T. If those three parallel lines intersect two transversals, we do have two different transversals that intersect those lines, lines L and M. Then what do? They divide the transversals proportionally. Meaning if you look at these sections that they split the transversals into, those are proportional. So if I look at, for instance, UW, that segment, and I compare it to the littler part of that transversal, WY, that should be the same proportion as looking at this transversal, doing the larger portion to the left, VX, and comparing it to the smaller portion to the right, XZ. So the way those transversals are split by the parallel lines is proportional as well. I could have also written it as UW and compared to the larger section of the other transversal, VX, right below it. And then start with the smaller section of the first transversal, WY, compared to the section below and the other transversal, XZ. You notice these are the same because these diagonals are exactly identical. I just flipped around WY and VX. Okay, so three parallel lines split by two transversals split those transversals proportionally. And this other theorem has to deal with an angle bisector. It says if a ray bisects an angle of a triangle, notice this ray, CD, does bisect the original angle ACB of the triangle. How do I know it bisects? Because it cuts it into two congruent angles. Therefore, it is an angle bisector. We have two congruent angles there. Then it divides the opposite side, meaning this side that it intersected, into segments whose lengths are proportional to the lengths of the sides. Now what I'm looking at here is it's dividing this whole entire side into two portions, into a portion from A to D, into a portion from D to B. And the portions of those sides are proportional to the sides nearest them. So the way that an angle bisector splits this side is proportional to the sides nearest to them. So if I want to look at side, I shouldn't say side AD, the portion of that side AD where it was split by the angle bisector, I would compare that to the side nearest to it, which is side AC. And that ratio is going to be exactly identical to the other portion of the side where the angle bisector split, which is DB, compared to its side of the triangle it was nearest to, which is CB. So it's kind of neat. If you have an angle bisector, which I do here because these angles are congruent, I look at the portion from the angle bisector back to the vertex, compare it to its side, and that's the same ratio as the portion from the angle bisector to the vertex compared to its side. So two more proportionality theorems today. Let's practice them. Now, okay, in this example, I have, well, it looks like streets, huh? First Street, Second Street, and Main Street. I have the distances here between these streets. I'm going to have to find X. Now remember, for that first theorem, you need these three lines to be parallel. Are they parallel? Well, if I have congruent angles marked here, what kind of angles are those congruent angles? If you think about it, these are all corresponding angles. And if we have corresponding angles congruent, which we do here, we know that the lines are parallel. Corresponding angles are congruent, lines are parallel, so I do know that all of these are parallel since the corresponding angles are congruent. That's corresponding angles converse. That says those lines are parallel. So now I know that these transversals, or these other streets, are split proportionally. So I can compare 160 meters, well, I can compare it either to the other part of that same road, 320, or I can compare it to the portion on the other road that corresponds, which is X. It's kind of up to you. Maybe I'll do 160 to X. I went top to bottom here. in between the same two parallel lines. So I'm going to go top to bottom here in between these parallel lines. So 320 to 340. And now I can find this distance x, which I'm assuming, since this was a little bit more than this one, should be a little more than 160. I'll find that by cross multiplying. So I get 320x equals, I have to do 160 times 340. I get 54,400. And I divide that by 320 and find that x equals 170, which seems very reasonable for that length. These were all in meters. So I found x. So looking at three parallel lines cut by two transversals, and those transversals are split proportionally. So I could set up that proportion and solve. The one below here is looking at, oh, look at this. This is an angle bisector, isn't it? Because of the fact that I have two congruent angles, this is an angle bisector. So therefore, if I look at the two sections of the third side that it intersects, those are proportional to the sides they are nearest to. The only problem is I don't have a name for this portion of that segment. 40 was the entire thing, this entire third side. X is this portion here. Well, if I knew that this was, say, 25, I don't know. If I knew this was 25, how would I find this portion? Because that's what I'm looking for. Wouldn't I take 40 minus 25 to see what's left for this, and it would be 15? So shouldn't this be the entire length of 40 minus or take away whatever that length of x is? That's what you'd have left for here. So now that I have a name for that, I will be able to set up my proportion. I know that this portion of that third side, 40 minus x, in comparison to the side that it's nearest to of that triangle, which was 24, is the same ratio as the portion of this side that was split by the angle bisector, which is just x, compared to its side that it's nearest to, which is 32. Okay, so there's my setup. Could I flip these fractions around? Could I do side of 24 to its portion, 40 minus x, equals this side of 32 over x? Yeah, that would just be flipping both fractions. Could I even look at the sides left to right and do 24 to 32 equals and go left to right on the side that's cut, 40 minus x over x? Yes, you'd still have the same things diagonal. So a lot of ways to set it up again, just being careful that it works. Let's solve this one. I got to cross multiply. I'm going to have to do some algebra here. This way I just get 24x. Here I have to do 32 times, and this will equal 32 times the quantity, so in parentheses, 40 minus x. And I get 24x equals 32 times 40, just to check that, 1,280, minus 32x. And now I have x's on both sides, so I'm going to add 32x, get rid of it here, add 32x here. So 24 plus 32 would be 56x, equals that 1,280. So I will divide 1,280 by 56. And it looks like x equals 22 point, I'll go to two decimal places, 86. So not the best number, but it works out there. All right. In plugging this back in, if this was 22.86 going up here, if I do the 22.86 divided by 32, I could even check this decimal as a fraction. I'm getting like 0.714. And I could plug it in back here and do 40 minus 22.86. I'm going to hit equals, I'm going to divide that by 24 and see if I get the same decimal. Yeah, it's that 0.714-ish that I'm looking for. Okay? So a little bit of trick trying to figure out what to call this portion of that segment. But again, an angle bisector splits a third side into parts that are proportional to the sides nearest to them. Now I want you to use these proportionality theorems on this last example. This is going to be your homework actually for tomorrow from the notes. I want you to have these done. Let's talk a little bit about them before I let you go on them. if you notice here, I have 3 right angles marked. And these right angles are corresponding angles, or I mean, you can consider them, since all of these are right angles, you have alternate interiors, alternate exteriors, etc. But it does make these lines parallel because of all those right angles. Now that the lines are parallel, you know that these sides, these transversals, are split proportionally. Set a proportion, find x. In this example, I have a right angle marked for the whole angle. I know this is 45 degrees. What does that make this angle then? If this whole thing is 90 and we have a 45, this would have to also be 45 degrees. So now don't I know that if this is 45 degrees, then these 2 angles here and here, aren't those congruent? Therefore, this is an angle bisector, so it does split this side into 2 parts that are proportional to the sides they're nearest to. So I want you to solve for x in both of these. This is your homework for tomorrow, looking at 2 more proportionality theorems.